we're going to start with the total change theorem, which involves an integral. Okay, so the total change theorem says from A to B. Now this is the sentence that describes the answers that we've been finding. Okay, f prime of x. Okay, notice that this integral, it's not the original function I wrote here, it's the derivative equation. It's still just a graph, okay? But it's the units that we're going to pay attention to. Okay, so this is the rate equation. Rate equation. Okay, and this represents the total change of f of x. Okay, now that is the original in units. Okay, so this is, we'll say, units per time, right? It's a rate, miles per hour, people per minute, right? It's just a rate. Gives you the total change, original units. Notice that if you take a rate, say velocity, and you multiply it by time, you get distance. Look at the units here. Okay? Now, the next question, or the statement, is an initial value problem. So we're going to say f of 0. Okay? This is your S naught, or initial position, or initial value. Your starting value, that's where the 0 comes in, plus the amount of change. Okay, starting value plus the amount of change from 0 to B equals I feel like saying it equals f of B, which is the ending value. The starting value plus the amount of change equals the ending value. Remember that this integral here represents the total change, and I'm going to add something for specifics, from A to B. The integral represents the amount of change. Starting value plus change equals ending value. And that's what we're going to look at today, is how do we use our units to answer the types of questions that are going to ask for the amount of change, or potentially the starting or ending values. All right. First question, and let's see how these two statements are used. A car comes to a stop 5 seconds after the driver slams on the brakes. While the brakes are on, the following velocities are recorded. Estimate the total distance the car took to stop. All right, I'm asking for total distance. What kind of units is a distance unit? Meters, or in this particular case, let's say feet. Okay, how many feet did it take the car to stop? How are you going to get to the units of feet from the units that are given to you? What do you have to do to those units to get feet? Multiply them. That's a definite integral. That's how you decide what you're doing. You're looking at the units. The question says, how many feet? Okay, look at the information given. I have to multiply my units. That's the definition of the definite integral. Okay, so we're going to write the integral down here. We'll do the integral on the left side here. From 0 to 5. Okay, 0 to 5, velocity dt. And then on the other side, we're going to sketch a little picture so that we can see what this is. So 0 to 5. 0, 1, 2, 3, 4, 5. Okay? And it does not have to be perfect, just rough estimates here. Now my y values look like they start at 88 and then they go down to 0. All right. So okay. Right. The values are right here in front of me. I'm just rough picture so I have an idea of what this looks like. If this is the integral that can be used to find the total distance, right, total feet, it says use the division given in the table and 5 uniform right and left rectangles. Okay, so let's go ahead and pick, I'm pretty sure we're just going to do the right rectangles. I don't know why left is still there. Okay, right rectangles. Here's your sketch of your picture. Draw the right rectangles so we can see what kind of area calculations we'll be needing. Right, you want to just connect the dots with a curve so it's easier to draw your rectangles. Okay. So you should have 5 rectangles. Uniform width, are they all the same width? Yeah, okay. So I followed the directions. I have 5 uniform width right rectangles. Now do your calculation. In this case, I'm not actually looking up any values for my calculator. It's just a picture that's given to me, and I have the coordinates. 60, 40, 25, 10, and 0. Those are my y coordinates. They're already in the table. Okay. Approximately 1, 2, 3, 4, 5. 5 rectangles. Write down the area of each. I'm just jotting down my area formula. Okay. I want to make this a little neater. 1, 2, 3, 4. There we go. First rectangle is, all right, delta x times y. 1 times 60. 1 times 40. 1 times 25. 1 times 10. 1 times 0. And then let's figure out what that number actually is. $135? $135. Now, you need units, right? Today is about the units. This one was seconds. This side was feet per second. Multiply them because it's the definite integral. You get feet. And then we're going to write the sentence that actually answers the question. Estimate the total distance the car took to stop. The car took a total of 135 feet with units to stop in 5 seconds. You should be including both something about the Y number and the X numbers, right? I only looked from 0 to 5 seconds. Okay, this time let's just do the trapezoids. Okay, so we're going to sketch a picture, just a rough picture, so we have something to draw your shapes with. Okay. Coal gas is produced at the gasworks. Pollutants in the air are removed by scrubbers, which become less and less efficient as time goes on. Measurements are made at the start of each month, although some months were skipped, showing the rate at which the pollutants in the gas are as follows. All right, so we have 0 to 1 to 3, 4, 6, 7, 9. All right. Let's use our divisions in the table. 0. So I need to go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And 0 to 20 looks like the highest. Okay. 0, 5. 1, 7. Oops, skip. 3, 8. 4, 10. Okay. 6, 13. 7, 16. And 9, 20. Okay, there's a rough sketch of the points that I was given. Just sort of connect the dots. I don't actually know what this graph looks like. I just kind of connected the dots so I had an idea. Looks like it's mostly increasing. Right? A little faster in some places than others. The question should be, how many tons escaped in 9 months? How many tons escaped in 9 months? Well, I have months here, and I have tons per month here. If I multiply my units, I get tons. The units are going to answer the question for you. I'm asking for how many total tons. Then whatever you do with your units needs to give you tons. That's a multiply your units. That's why you need the definite integral. In order to get from the graph of the information you were given to the units of the answer, you have to multiply them. So from 0 to 9, R of t, notice that is the rate, is approximately. I already know the answer is supposed to be tons. You shouldn't be guessing the answer. It's asking for it. Now I did say 3 uniform trapezoids. Now I'm going to delete the word uniform. I just want 3 trapezoids divided up with our data and divided as evenly as possible. I have 1, 2, 3, 4, 5, 6, 7 data points. 3 data points per trapezoid. If I want to split this data as evenly as possible into 3 sections, that's 3 data points per trapezoid. Now eventually, we don't want to have to draw the picture. Okay? The picture is just to help you visualize what you're doing. My first trapezoid starts here at 0 and goes all the way over to 3. Notice that my lines are pointing at the values. My second trapezoid goes from 3 to 6. Notice how the data in the table is being evenly divided. I'm not dividing the numbers up. I'm dividing the number of points in the table. That's what using the values in the table looks like when you're dividing it evenly. 3 data points per shape. Okay, trapezoids, so let's remember that area formula. Okay, 3 of them. 1, 2, 3. You want to look the numbers up in the table? Or do you want to write them on the graph? That's up to you. Here's my first trapezoid. Here's my second trapezoid. Here's my third trapezoid. Okay, see what you can do with that trapezoid formula. Look at the points that you're using. Label them if you need to. Okay, you should be able to come up with 100.5. Turn this area formula into our trapezoid. So that's over 2y1 plus y2. Now, eventually, I would like you not to have to draw the picture. Okay, you should be able to do this just from the table of values. Right, notice I double circled the middle values because I'm going to use them twice. One for the first trapezoid, once for the second. Once for the second, once for the last. Okay, now my delta x. You got to actually look at it. From 0 to 3. So my delta x is 3 over 2. 5 plus 8. My next trapezoid. 3 to 6. 8 plus 13. My next trapezoid. 6 to 9. 13 plus 20. Okay, try to visualize this without actually drawing the graph. You shouldn't need the graph in order to write down the area formulas. Okay, when you're ready, turn it over so we can look at question 3. One more. All right, 3 uniform midpoint rectangles. Now I'm going to delete the word uniform. I want 3 evenly spaced midpoint rectangles using the data that I have. Okay, look at the number of values. We have 1, 2, 3, 4, 5, 6, 7. I need the 7 data points split into 3 even sections. But keep in mind the edges get used twice. 3 even sections. That means that each of them get 3 data points. When you have a table of values, you're not doing a delta x so much because the points don't have to be spaced nicely. Right? You're looking to divide up the number of points evenly. Okay, so let's see. We need 3 midpoint rectangles. We are running a marathon. Oh, this one's interesting. We have minutes and miles per hour. Okay. And time spent running, so it looks like 90 minutes. Okay. The data, assuming Roger's speed is always decreasing, estimate the distance that Roger ran in the entire race. Okay, well, let's see what we get. Hopefully, if he's running a marathon, it should be close to 26.2. All right. After an hour and a half, he is exhausted, so he stops. Let's see how long he ran before he stopped. Okay. Midpoint rectangle. So we're going 0 to 90. Speed. Right, I'm going to call it S for speed. Notice it's a rate, though, miles per hour. It's always a rate that I'm putting here. dt is approximately. All right. Can you do it without sketching the graph? Say it again. Midpoint rectangles. Midpoints. Oh, midpoints. Midpoints of the edges. Middle of the, not the left edge, not the right edge, the midpoint. Notice I starred the midpoint up there. That's what I'm looking for. And so I'm going to kind of extend my little, it's almost like I drew my rectangles right there on the graph. But I need the middle. And so I'm going to circle the y-coordinate that I need to use. I need the middle coordinate. I'm not averaging anything. I just need the middle x and its corresponding y value. Twelve, 11, 10, 8, 7, oh. Oh, I missed it. 10. Yeah, there is something different about this question. There we go. I'm sketching it just so that you can see it, but I'd like you to try to do it without having to draw the graph. Here's my 3, right? Evenly spaced data points. Then I'm like, oh, I can see the middle coordinate. It's this one. Corresponds to 15 and 45 and 75. those are the values you're looking at to make your midpoint rectangles. Okay, rectangles, that's just delta x times y. All right, I've got minutes here, and I've got miles per hour here. Which doesn't quite match up very nicely. Hours and minutes don't actually cancel out. And so we're going to have to look at your units. So we're going to have to do a little bit of converting here because my units don't quite match to begin with. Now it still works because it's a rate times time. That's still distance. Well, we're going to have to convert it. Okay, 3 midpoint rectangles, 30 times 11, plus 30 times 10, 30 times 7. So we end up with 840, right? No? Yes, 840. I'm not going to put units on it quite yet because I need to convert them. I'm going to convert them down here because I'm a little bit out of space. So I've got 840. Now I multiplied miles and hours times minutes. That's what I did. But I need my answer to be in miles. How far did he run? He ran this many miles. All right. Well, do a conversion. You are mostly seniors in high school. Convert. How are you going to do that? Yep, so I'm going to put hours here, and I'm going to put minutes here. You figure out what number you need to write there. Why do I do that? So then my units cancel out. Okay, you figure out what numbers you need to put here, and then write down your final answer. Miles. Look, what's left? Just miles. Just miles. Just miles. Okay, so we get 1 hour is 60 minutes. So I divide, and I get 14 miles. So he ran 14 miles in 90 minutes, and that was too fast, and he was done. Not bad. That is kind of fast, but not far enough. All right. The next question has no units. On number 4, see if you can set up the right area calculations. Look very carefully. Okay? I'm going to tell you. Look carefully at the delta x's. Now I told you how many rectangles to make. You look very carefully at what the delta x's are supposed to be. See if you can set them up. Draw a picture if you need to, but see if you can imagine doing it without that drawing. Try to. You can still sketch it. It's just 5 points. Right? But you should work on trying to do it without having to draw. That means your rectangles. Right, it doesn't say uniform, it just says use the data that's given to you and divide it up into 4 slices. Oh, it starts. It's gonna be different. Does it say uniform? No, which means they can be as wide or as narrow as needed by the values in the table. And so I'll do one picture, 0, 1, 5, 6, 8. Okay, roughly there's my numbers. So we get 2, 3, 4, 5. Okay, 0, 2, 1, 4, 5, 2, 6, 3, and 8, 5. All right, and so I'll just very light, and now I have no idea if this is what the graph looks like, but that's about right. It says 4 rectangles, which means using the data values given, you still have to make 4 slices. They're not evenly spaced. It didn't say evenly spaced. It just said 4 slices. That's it. And so 4 left slices, which means I need this value, and this value, and this value, and this value. That's it. Those are the only 4 rectangles I need. And I'm going to circle the same values in my table. Those are the y coordinates that you need. Okay, and then I'm going to sort of make my rectangles. So we get this one left, okay. We get this one left, this one left, right? 4 left rectangles. Then I have to figure out how wide each rectangle is. What's your change in x? Well, it's a 1, and then it's a 4, then it's a 1, and then it's a 2. And I can see that based on the diagram I have. My delta x is 1, and then it's 4, then it's 1, and then it's 2. So we are looking at approximately, my first rectangle is delta x times 2. Delta x, so from 1 to 5, that's a 4, but it's 4 high. Okay. Next, from 5 to 6 is 1, and it's 2 high. The next one is from 6 to 8, so it's 2 wide, and 3 high. And if you're looking just at the values in the table, you can pick that out. Sometimes here I drew my rectangles below. Sometimes I like to draw my rectangles above the table. Helps me see the change in x. Right, try to get to it without actually graphing it. End up with approximately 26. it doesn't say that and you're like averaging your acceleration, you're getting an answer. It's still an estimate. It's a different estimate. Okay, so let's see what the second one looks like. Okay, it's actually the same picture, right? Same picture, except this time, look at what I'm circling. It's the right endpoints. Look at the table. Left circles, right circles. Left rectangle, right rectangle. Okay, so approximately. Now my delta x isn't changing. Oh, they're almost the same value. Sorry. Okay. 0, 1, 5, 7, 8. Almost the same. 3, 2, 3, 2, 4. Right rectangles. 1 and 2. 4 and 3. 2 and 2. 1 and 4. And we get approximately 22. Okay, last one. 2 midpoint rectangles. Well, I have 6 data points. I need to divide them evenly. Notice that my edges, I'm sharing a side. When you draw your rectangles, you are sharing a side at those dividing points. So they each get 3 data points. And then I need the midpoint. So I'm going to circle the midpoint y value. And right up here, I'm going to label my delta x. 0 to 3. 3 to 8. You should be able to pick out the information from just the table. This is how I prefer to draw my rectangles, right across the x's, so that I can see the delta x very clearly, and then I can pick out the left, middle, or right endpoint. Because it says 2, so divide the data points into 2 even sections. Not how wide they are, just 3 data points each. Question? The middle x coordinate of whatever you had. You can't add, we're not averaging anything. I'm not going to say 1.5 because 1.5 is not in my table. You're going to have to take the middle of whatever is available. The middle x. Now when you have an equation, we do it exactly because I have it's a continuous function. I have every value I need. In this particular case, you have to take the middle-ish of what's available, wherever that middle happens to occur. That's right. When you have a limited amount of information, that's what you have to do. 0, 1, 2, 3, 4, 5, 6, 7, 8. 3, 2, 5, 4, 8, 6. And connect. Okay, so there it is. There's my midpoint. And what happens is, notice that here was a little bit, I'll shade the actual area. It works out. Some of it's under, but some of it's over. Right? You still get a reasonable estimate anyways. But you have to take the middle of what's available to you, which means the middle data point. It's not going to be the exact midpoint because it's not a continuous set of values that we have. I can't pick 1.5. I have to pick the middle of whatever was available to me. So if you have 3 data points, you pick the second data point. If I had 5 data points, I would pick the third data point, whatever the middle data point is. Okay, so we get 3 times 4 plus 5 times 4, 12, 32? 32. Okay, that's where we're going to stop. Okay, we will pick up